Okay, let's go to AC circuits in parallel. As we know, when we're dealing with circuits in parallel, the voltage is constant and the current is the sum of the current through each branch. Great. In this analysis, we do the same thing as when we have in a series, circuits in series, right? We're looking for the relationship between the voltage and the current. As we know, when we are dealing with AC current, the current and the voltage changes at any time. We're dealing with a simple harmonic motion, correct? In this case, we represent the voltage at any instant to be equals to V, which is the maximum, right, voltage, or the amplitude of the peak voltage, right, times cosine omega t. Great. Now using this this value for voltage, let's find the current, right, when we're dealing with resistors only, when we're dealing with capacitors only, right, inductors only, or when we combine them. Okay, let's do it. Also, let's find the average power for each case. Great. Let's start with resistors in parallel. Imagine that we have this the source. This is the source, and we have these two resistors, and these are in parallel. Perfect. Imagine this is the resistor 1, this is the resistor 2. Of course, this is current 1, and this is current 2, and this is the total current, and this is the voltage, instantaneous voltage. Perfect. Now let's find the current, right, and see how it's related to voltage. Let's do it. So how do we define the instantaneous current? Well, it's gonna be according to Ohm's law, or Mrs. Ohm's law, is equals to voltage divided by resistance. What is the voltage? Well, we're taking this to be the constant voltage through these two resistors, and what do we have? Gonna be the maximum, correct, times cosine omega t divided by R. What is this? Again, using Ohm's law, it's gonna be the total, right, or maximum current. It's gonna be the total in this case, the total current. Perfect. So we can define that the instantaneous current is equals to the total current times cosine omega t. As you can see, right, these two are in phase when we're dealing with resistors only. And what should be the phasor diagram? The phasor diagram is going to be represented, right? Imagine this is the current and this is the voltage. This is, or we can do it, yeah, we can do it this way, current and voltage. Remember, as we did for circuits in series using AC current, we mentioned that the projection of the current, the maximum, onto the x-axis is the instantaneous current, and the projection of this maximum voltage onto this x-axis is going to be the instantaneous voltage, right? And remember, this is the phasor diagram. Then we have that these two quantities, right, move in a counterclockwise with some frequency omega, correct? Perfect. And this is the frequency omega, the phase omega t. Great. What about the current? Well, what should be the total current? Well, current is equals to, in this case, we are dealing with the maximum current. Perfect. Remember, the maximum happens when this quantity cosine is 1. When that is 1, right, we have the maximum current is gonna be this quantity, right? It's equals to, in this case, the total is equals to what? Current 1 plus current 2. Well, what is current 1? Well, remember Ohm's law. We can find that current is equals to voltage divided by resistance. In this case, we have this voltage. Voltage is constant, right, in parallel, divided by resistor 1 plus voltage divided by resistor 2. Correct? Perfect. And what should be the resistance? Remember, when we're dealing with circuits in parallel, well, resistance, the equivalent, we call it equivalent of the total resistance, is equals to 1 over R1 plus 1 over R2, right? And so on. In this case, we have only two resistances. So it's going to be 1 over R2 inverse. Also, we can represent that the total resistor or the equivalent resistance equals to voltage divided by the total current, correct? And this is again the relationship between voltage and current when we're dealing with resistors only in AC circuits in parallel. Perfect. So one more time, we have that the total current is equals to V over current 1 plus V over current 2. Correct. Great. Now let's go to the case when we have only capacitors. Okay, let's do it. Only capacitors. Perfect. When we have only capacitors, right, we have to derive an equation for current. Okay, let's do it. Let's do it. So imagine that we have, again, this is the source. Now we have capacitor 1 and capacitor 2. Perfect. Capacitance 1, capacitance 2, correct? And this is the instantaneous voltage. Perfect. Now let's see what happens when we're dealing with capacitance. Remember, how do we define capacitance? It's equals to charge divided by voltage through the capacitor. Correct? Perfect. Now let's define for voltage through the capacitor. Correct? It's equals to what? It's equals to, in this case, charge divided by capacitance. But from the condition that we have at the beginning, this is equals to voltage to maximum to the capacitor, right? The amplitude, correct? Times what? Times cosine omega t. Remember, we're looking for current. We already found voltage, right? What about current? Well, how do we define current? Well, remember that current is defined as change the derivative of charge with respect to time. We have charge right here. Now let's do it this way. Let's find the derivative of this voltage to the capacitor, right? So it's equals to what? This derivative with respect to time, correct, times 1 over c, correct, equals to the derivative of this quantity, cosine omega t, correct, with respect to time. Perfect. Now let's do it. We already found, right, this quantity is gonna be I, right, the instantaneous current. Now let's derive this quantity, and what do we have? Well, we have that I, in this case, gonna be, this is I, right, I over C, let me see, this quantity is equals to I, is equals to VC times what? Times negative sine omega t, correct, times omega. Perfect. Or we can arrange it this way. The instantaneous current is equals to negative VC, right, omega c sine omega t. Or we can also represent this in this way. This is equals to VC omega c, correct, cosine omega t plus pi divided by 2. Now, when we compare this quantity, which is the function of cosine, to the quantity of voltage, which is also cosine, we can see that there is a difference in phase, pi divided by 2. Right? Perfect. So we found then for a capacitor, the instantaneous current is going to be equals to this voltage to the capacitor correct? Omega times capacitance times cosine omega t plus pi divided by 2. Correct? Or we can use a negative sign, that's right here. Great. Now let's find the maximum current. When do we have maximum current? Well, when this quantity cosine, right, of this angle is 1. In that case, what do we have? That the current, the maximum through the capacitor is equals to what? Is equals to the voltage to the capacitor times omega c. Perfect. Now let's use again current using Ohm's law. Remember, current is equals to voltage over resistance. Now when we compare this quantity to this quantity, we can also represent by current in the same way as we use Ohm's law, right? So current is equals to voltage through the capacitor divided by the quantity that represents the resistance. Remember from the previous chapters, we know that this quantity is called reactance, right? In this case, it's gonna be the capacitive reactance, right? That has the same unit as resistance, ohms, correct? Well, and in this case, when we compare now this and this, we can see that this reactance of the capacitor is equals to 1 over omega c. The same thing as for a series case, correct? Perfect. So we have now that current through the capacitor is equals to the voltage to the capacitor divided by the capacitance. Correct. Divided by the capacitive reactance. Perfect. Where this capacitive reactance is equals to 1 over omega c. Perfect. Now let's see how we represent this using the phasor diagram. Okay, in the phasor diagram we have that this is the current to the capacitor and this is the voltage, right? The voltage of the source, the voltage to the capacitor, because it's constant. Remember, voltage is constant. Perfect. And we can see that in this case the voltage to the current is leading, right, the voltage, correct? And also I will represent this in this way. This is capacitor, right, current through capacitor 1, correct, plus current through capacitor 2. This is the total current. How we can find the total current? Okay, and there's gonna be, well, maybe let's leave this in this way. And remember, what should be the total current? One more time, is equals to current 1 plus current 2. And what is current 1? Okay, voltage over the reactance, right? Capacitor 1 plus voltage over reactance capacitor 2. Right, and again, similar to this case, we have the phasor diagram, now using current in this way. So we have current 1 plus current 2 equals to the total current, correct? And this is voltage. So it's going to be current 1, right? This is current 2, this is the total current, correct? Parallel to this current to the capacitor. And again, we have this is 90 degrees, correct? Perfect. Now let's go to the case where we have inductors. Let's do it, inductors. Perfect. Let's go to inductors. Yes, correct. Again, this is current 1 or current through capacitor 1 or current through capacitor 2. And that's the total current, correct? Yes. Now let's go to the case when we have inductors. Okay, let's do it. When we have inductors, like in this case, we follow the same steps. It's inductor 1, inductor 2, right? This is gonna be L1, this is L2. correct? Perfect. Now in this case, we are dealing with the voltage through the inductor, but is defined to be equals to L, the inductance times the change in current with respect to time. But one more time, using the original equation for the instantaneous voltage is equals to V, well, the maximum, right, voltage through the inductor times cosine omega t. Okay, now let's work with this section right here, and let's rearrange this in this way. The I, right, L the I is equals to the maximum voltage to the inductor times cosine omega t dt. Now let's integrate. And what do we have right here? We have L times the instantaneous current is equals to voltage to the inductor divided by omega sine omega t. Correct? Also, this is equals to the voltage, right, over omega times cosine omega t minus pi divided by 2. Correct? So we have, now we can solve for the instantaneous current, correct? So the instantaneous current now is gonna be equals to omega L, right? It's gonna be VL over omega L cosine omega t minus pi over 2. Okay, and this is the case when we have now the current through the inductor is equals to this quantity, omega L, the inductance, right, perfect, times cosine omega t minus pi omega t minus pi divided by 2. One more time, let's compare current and voltage. Remember, that's the analysis for this section. We are comparing current and voltage for all the cases where when we have the elements of resistor, conductor, capacitors, and inductors. Okay, and we compare now, we can see one more time that these are out of phase by pi divided by 2. Great. And what should be the phasor diagram? Well, in this case, the phasor diagram is going to be in this way. This is the voltage, and this is the current through the inductor. Again, now this current is behind, right, 90 degrees, right, of this voltage. Perfect. Great. Now, what about the maximum? One more time, the maximum current. Well, the same thing as before. We make this quantity equals to 1, and we have that the maximum current through the inductor is equals to voltage through the inductor divided by omega times the inductance. And the same thing as before. Let's compare this to Ohm's law, right? Current is equals to V over resistance, and we have this form, correct, for the current through the inductor is equals to VL over this quantity that represents, right, resistance, right, it's gonna be the reactance, it's gonna be the inductive reactance. Perfect. Similarly to the case when we have circuits in series. Great. And we get then this equation, the maximum, right, is equals to VL over X L, where this reactance is equals to omega L. Great. Now let's find that third current, right? Let's find the third current because it's in parallel. Remember, the third current is equals to current 1 plus current 2. And what should be the current? We found it already using this formula. V through the inductor divided by the reactance through the inductor 1 plus the voltage, which is the same, right, divided by the inductance the reactance right through the inductor too. Correct? Okay, so we can have then that the total current is equals to, one more time, similarly, right, to capacitor, right? It was very similar to capacitors. We just did it before, correct? Plus this divided by this reactance to inductor 2. Perfect. And the same thing as before, correct? We can have, this is the current through current through inductor 1 plus current through inductor 2, right? This current equals to the total current, correct? This is current, okay, one more time, equals to the total current, which is going to be the total right here, computed here, and this stays the same, V. This is the phasor diagram. Great. Now let's combine them. Let's combine these elements. Let's do it. Let's do it. Now imagine that we have right here, we have a resistor and a capacitor, right? Let's do it. Imagine this is a resistor right here. We have a resistor and we have a capacitor. Okay, this is the resistor and this is the capacitor. Perfect, the resistor and capacitor. Great. In this case, let's use the phase diagram. Remember, when we combine all of them, by the way, all the elements, what do we have? When we combine up all the elements, we found that in this direction we have the current through the capacitor, in this direction the current through the inductor, and this is voltage, right? Or the current through the resistor, right? In this case also we can call it, right, current to the resistor. Perfect. Now let's see, when we're dealing with these two, so we're dealing with this quantity and this quantity. So what do we have? Well, in this case we have that is in the phasor diagram, that this is the current, right, through the capacitor, correct, and this is the current through the inductor, right, to the resistor, current through the resistor, correct? Perfect. Now what should be the total current? Well, the total current is gonna be in this way. And we can see, right, we can represent this quantity one more time using the instantaneous current. This equals to current through the resistor, right? I hat plus current to the capacitor, right, J hat, using vector notation. Also, we can use the magnitude as we did before, correct? Also, we can say that the total current is equals to, we can also the total right here, correct? Equals to current to the resistor I hat plus current, the magnitude, right, to the capacitor J hat. Of course, this is the angle phi. So it's gonna be the total. Well, how we can find the magnitude? Well, using the Pythagorean theorem, right? So the total is equals to square root of this square plus this square. Correct? Perfect. And then the same thing as before. Well, remember, when we're dealing with circuits in series, we found that Z, right, the impedance is equals to resistance in this direction plus this reactance, in this case gonna be negative the reactance in that direction. Correct? Perfect. Now we can again use this to be the total current, right, when we're dealing with a resistor and a capacitor in this way. Also, of course, we can find, right, that the current to the resistor is equals to V over R, and the current to the capacitor equals to V over, right, the reactance. The same thing as we did before. Right? Perfect. Now what happens if we have also one more time, what should be, we use this relationship that V is equals to current times Z, and also we can find Z in this way. Z, the total Z is equals to V over the total current. Right? This is total impedance. We can find it also in that way. Great. Now let's go to the case when we have a resistor and an inductor. Okay, let's do it. Resistor and inductors. Perfect. Imagine that's inductor. Right. Now we are dealing with this part right here. Perfect. What should be the total instantaneous current? Well, because this goes down, right, it's gonna be negative, correct, current through the inductor. The same thing happens right here, the total is gonna be negative, but this one stays the same, correct? It's gonna be through the inductor, It stays the same. And Z in this case is gonna be positive for this case. Okay, perfect. Now let's continue in this picture using the phasor diagram. Not gonna be in this direction, it's gonna be current through the resistor, gonna be current through the inductor. Correct. Perfect. And the equations are the same. Now what should be the total? The total current, well, the total current is gonna be in this way. Right, this is 5. Also, we were looking for the average power. Remember, it's the same formula as we got in circuits in series, right? And power, remember, was equals to, power is equals to voltage times current cosine phi. The same formula, the same equation. Okay, now what happens if we have all the elements together? Imagine now we have a capacitor 2 added to this system, right? Now let's add a capacitor, and we have all the elements that we are dealing with so far: the resistor, the inductor, and the capacitor. Okay, perfect. This is the LRC circuit in parallel. What should be then the total current instantaneous? Let's do it. In this case, remember, we have to use the general equation, the general phasor diagram. This is the current through the capacitor, correct? So you can see these two are in the same direction, the y direction is in the x direction. So this is equals to the current through the capacitor, correct, minus, in this case it's going to be plus right here, plus, correct, as a vector, correct, minus the current through the inductor in this direction. Remember, we're dealing with, this is the unit vector I hat and j hat, using vectors, unit vectors. Perfect. And then the same thing for the maximum current, correct? Well, the total current is equals to what? Current to the capacitor minus current to the inductor in that direction. Correct? The same thing happens for the magnitudes right here. The magnitude now is going to be equals to this, I'm still using the reactance as well. We're dealing with current, right? Current through the capacitor minus current through the inductor, current again, because in series we use reactances. Okay, current through the inductor square. Perfect. Perfect. The same thing happens to the impedance, right? This equals to impedance to the inductor minus impedance to the capacitor, right? J hat. Correct? Perfect. And that's gonna be then the total current where we're dealing with LRC circuit in parallel. Correct? Great. Now let's do the last one. We can use this in this case. Look, when we're dealing with these two at the same time, we have two possibilities. One possibility is that this one is larger than this, or the one is that this one is larger than this magnitude, right? Correct. What do we have then? Well, we have these two possibilities. One of them is this one, correct? This is gonna be the current through the capacitor minus current through the inductor, right? This section, and the other one should be in this case, right? This quantity is larger than this quantity. That's why we have the resultant going down. What happens if this is larger than this one? So the resultant is going up, correct? So in that case, we have again this condition is gonna be current through the capacitor minus current through the inductor, correct? This stays the same to the resistor, and we get again the maximum, the total current, correct? In this case, depends right on the values for these two quantities. But then, all right, is 5 for both cases. Correct. Perfect. Now let's go to the last topic in this section. Let's go to the case when we have this situation. Imagine that we have a resistor, and right here we have a inductor, and then we have right here a capacitor. Imagine this is a capacitor right here. This is a capacitor, and we have a resistor, and then we have a resistor, and we have another inductor. Okay, how do we work with this case? This is R1, this is inductance 1, this is capacitance, this is R2, right? This is R3, and this is L2. Oops, this is the capacity. Let's see what happens. Wow, how we solve this problem? How do we solve this problem? Well, in this case, we have that Z1. Okay, let's find Z1. Z1 is equals to, this is for these two are in series. We know what happens when we have quantities in series. So this is equals to R1, right? Plus the reactance for this inductor, right? J hat. What about the impedance through this branch? So we have this equals to resistor 2 minus the reactance to the capacitor, right, of the capacitor in this direction. What happens to the last branch is equals to resistor resistance to the resistor 3 plus, right, the reactance through the inductor 2, correct? J hat. Perfect. Now, what happens to the current? Well, remember we're looking for current 1, current 2. In this case, we have current 3. Current 1, current 2, and current 3. Perfect. And then we have current 1 is equals to V over Z1. Current 2 is equals to V over Z2, correct? This is Z. And current 3 is equals to V over Z3. Correct? Okay, perfect. Now let's find then the total. For each one, look, for each case, we have this situation. Let me see if I have room. Look, for case 1, where we have a resistor and the inductor. What do we have? Well, in this case, we have current to resistor 1, and then we have current to inductor 1. So what should be the third current? Well, it's gonna be the third current, right? The third current through 1, correct? This is the angle phi. The same thing happens to the next one. The next one is gonna be in this way. For this branch, we have capacitor, right? Current to the capacitor, and we have current to the resistor, and we have, this is the third current, right, for case 2. What about for the next one? For the next one, this is case 2. For the next one, we have current resist to resistor 3, right? And it's gonna be a current through the inductor 2, right? This is inductor 2. Current to the inductor 2. And what should be the total? What's gonna be, that's for case 3. Now, how do we find the third current? Well, the third current is gonna be equals to, let me do it right here. The third current is equals to, we have to add all of these 3 by using components, right? So we have current, right, through this component by this component by this component, right? So it's gonna be, this is in the let's say I hat direction, okay, plus current R2 plus current R3, right, in this direction, correct, plus, now we have in the y direction, correct, we have that this is positive, correct, it's gonna be current in the through the capacitor minus current through the inductor 1 plus current through the inductor 2. Correct. This is in the J hat. Right, and that's gonna be the third current. Correct. How we can find the third Z? Or the third impedance? Well, we add this plus this plus this in the let's say x direction, this plus this plus this in the y direction. Using vector notation, it's easier. Correct. Then we get in this way the total impedance, and also we can relate them in this way, right? The voltage is equals to the third current, right, times the total impedance. Correct. This is current total, right? Impedance total. And we can start also from here, right? By the total impedance. Correct. Great. And this is a this is the case when we have AC circuits in parallel. We're dealing with these 3 elements: resistor, capacitors, and inductors. Great. With this, we finish this analysis and see you in the next video. Thank you. Bye.